from the potentiometry instrument, you see that we need the reference electrode, which must have the constant potential for any current that can occur or apply. Although in this technique we don't generate the current, but you still need some like electron flows, right? Because you need to construct the electrical circuit, but it just have to be really high resistance. So to be safe, you're just gonna need some reference electrode which have constant potential for any current that can apply. And this properties is called ideal non-polarized stable electrode. This is a very important word. Ideal non-polarized stable electrode. Polarized stable means that if you apply the potential, if you apply the current, then the potential is gonna change. But here, this is non-polarized stable electrode. If you read this graph, you can draw it. If you read this graph, this is gonna be the graph between the current and the potential, I versus E, current versus potential. Here you can see that the graph of this, we call it IE curve. The IE curve of this reference electrode is basically vertical. It's basically vertical. This means that at any current, any value of current, either positive or negative or even zero, the potential of this non-polarized stable electrode is going to be constant. So this graph denotes the properties of the ideal non-polarized stable electrode, which is desirable for any reference electrode. And at the end, I show you the deviation of the non-polarized stability. This is kind of start to be polarized, but most of the time that should be non-polarized stable, which means that it has the constant potential, which is the desired properties of the reference electrode. So what are the requirements of good reference electrode? So the first one, I already told you, right? The known and constant potential. And the second one, it should be insensitive. It means that in addition to any current that can occur, if you change the solution, if you change the sample solution, for example, if you change the solution from acid to base or some weird kind of salt, the electrode potential of this reference electrode should be constant as well. Its electrode potential should be insensitive regarding to any solution, any sample solution. It should be insensitive. And the third requirement that it should be rugged. It means that you can it should be like easy to use, and it's kind of, you don't need to like clean it too much, something like that. And the first requirement here is that it should be easy to assemble. What do I mean by easy to assemble? So let's consider our maybe familiar reference electrode, which is the SHE, right? Standard hydrogen electrode. Now we say that standard hydrogen electrode is the standard electrode for to communicate other electrode potential. For example, like copper to iron, copper has a 0.34 volts versus SHE electrode. But it turns out that SHE is not ideal, because in order to use to construct the standard hydrogen electrode, you need the platinum sheet or platinum wire, which is expensive. Then you need the hydrogen gas with constant atmospheric pressure, like 1 atm. And you should know, right, that hydrogen gas is kind of dangerous. It is explosive. So having hydrogen gas in your reference electrode is not gonna be easy to assemble. You need the gas tank, and you need like a lot of line to build this. So standard hydrogen electrode is not the ideal reference electrode. But we use the standard hydrogen electrode just for the sake of the definition of general electrode potential. So what are the common reference electrodes that we use in electrochemistry? So we have basically two reference electrodes. The first one, let's see. The first one is called saturated calomel electrode, or we use the abbreviation SCE, saturated calomel electrode. let's see, let's consider this drawing. So the component of this saturated calomel electrode. So you have the electrical wire, maybe the platinum wire, because you still need the inert wire, like you need the platinum wire as the connection. But the main component is called you have the mercury as the liquid. You have liquid mercury. You have mercury 1 chloride, which is calomel. We call it calomel because mercury 1 chloride is called calomel in the past. I don't know why they named it calomel, but that should be good to know. So you need mercury, liquid mercury, you need the calomel, and you need the solid salt of potassium chloride mixed together as like this paste. It may be paste, I think, or it may be the solid one. Yeah, this is gonna be the mixture of these three components. And then this electrode will be filled with potassium chloride solution. It's basically in order to keep the equilibrium of this mixture. And then you need the porous plug because you don't need it to be leaked, right? You don't want it to be leaking with your sample solution, or you don't want your sample solution to contaminate your expensive reference electrode. So this is the actual thing. This is from a HANA instrument. This is the saturated calomel electrode. The size is gonna be like, I think, the 15 centimeter ruler, yeah, something like that. So yeah, this is a platinum wire. This is the solid mixture of the mercury, calomel, and potassium chloride. And you fill it with the KCl solution, and you have the porous plug at the end. So based on this component, you can write the shorthand notation of this reference electrode to be mercury, right? Because you have mercury here, mercury, and then vertical line, and the calomel, mercury, the calomel here, and sometimes it's liquid, sometimes it's solid. So people tend to put like saturate, but it's fine. You can just put calomel, and then you have KCl solution. So you put KCl with the amount of concentration that you have. And it is important to specify the concentration. I will explain later. And the reaction, the half reaction of this saturated calomel electrode is this one. So basically, mercury chloride, the mercury 1 chloride in solid, will receive 2 electrons, and you will get mercury liquid and chloride ion as the product. So if you consider this mercury, chloride, and calomel are all in this solid and the solution, which is the component of the saturated calomel electrode as well. And we need to control the amount because we need the same equilibrium. And if you write the Nernst equation, you will see that the electrode potential of the saturated calomel electrode will depend on the KCl concentration. That's why I put X here, which means that you have to specify the concentration of the saturated calomel electrode. But we commonly use the saturated KCl. The saturated concentration is about 4.2 molar, I believe. It's about 4.2 molar, but the saturated KCl will give you the electrode potential of plus 0.244 volt versus standard hydrogen electrode. And this is like the first in the history of electrochemistry, the first electrode to use because it is more stable. It is very stable, yeah, but it is less stable at high temperature because this liquid can be evaporated or the component can be changed. But and the mercury, of course, is toxic, as you should know. So after that, I think we use something else. So this is good to know because some people still use the saturated calomel electrode because it's stable. But now we kind of use something else. And that something else is the silver chloride electrode, the right column in your handout. So what is the component of the silver chloride electrode? So here you can see that it uses the silver wire here, use the silver wire. And then a part of the silver wire will be coated with silver chloride solid, right? So if silver chloride is the insoluble salt, so it has like white-ish or grayish color. So it's coated on the silver wire here. And of course, because the equilibrium needs KCl, so you put KCl solution with known concentration inside it, and you have the porous plug. Similar to the standard calomel electrode, if you think we just change the solid component from the calomel and mercury to be like silver and silver chloride. That's why we call it silver chloride electrode. And the shorthand notation of this electrode is silver chloride saturated and KCl. And again, you need to specify the concentration. And the half reaction is silver chloride, except one electron turns to be silver solid and chloride product. We work on this equilibrium, right, last time. And the potential, the electrode potential of the silver chloride electrode when you use the saturated KCl is 0.199 volts. And these two numbers, you're gonna use these two numbers a little bit, like the 0.244 and 0.199 volt. If the exam is closed book, then I will give you the number. If it's open book, then you should be able to find this number, right? You know where is it on your hand, in your handout. And the advantage of the silver chloride electrode compares to the mercury electrode, the calomel electrode, is that silver chloride, of course, is stable at higher temperature, and it is less toxic. I didn't say that it's non-toxic, but it is less toxic than mercury. And if you read the electrochemistry research, or if you go to purchase electrochemical equipment, then over 95% gonna use silver chloride electrode. So, but it's still important to know both electrodes. So is there any question on these two electrodes? All right, so let's go to the next one. So we said I give you the electrode potential when it is saturated, the KCl is saturated. But this table, on this slide, I show you the effect of temperature and concentration of the KCl on the electrode potential. And you can see that the temperature change, the electrode potential change, of course, the concentration of KCl in calomel, this is like 0.1 KCl in calomel, 3.5 KCl in calomel, saturated KCl in calomel, or 3.5 molar KCl in silver chloride, saturated KCl in silver chloride electrode. You can see that the potentials change. Let's do like this one, like 3.5 versus saturated. At 25 degrees Celsius, the electrode potential change from like 0.205 to 0.199, which seems to be not too much, but if you measure the very like trace concentration in picomolar or nanomolar, this is very huge. So it is good to know the state, to know the concentration. So if you communicate with people on your reference electrode, you need to specify the concentration. But in this class, we can like assume that we use saturated KCl all the time. So if I give you the problem on like use the silver chloride to calculate something, you just use the saturated KCl value, which is like 0.199 volt. So now you basically know three kind of reference electrode. The standard hydrogen electrode, that's for the definition, the sake of definition. The mercury chloride, the calomel, right? And then the silver chloride. So what you must be able to do is you must be able to convert between these three reference electrodes. What do I mean by that? For example, let's do this number line. We know that the electrode potential, the standard electrode potential of copper to iron and copper is 0.337 volt. But this number is against standard hydrogen electrode. So what is the standard electrode potential of copper to copper electrode? Measure against silver chloride and measure against saturated calomel electrode. This is very important that you should be able to do, like to convert the reference electrode from the She to silver chloride and to saturated calomel. So let's see. This is like basically arithmetic, but it may be a little bit confusing because you have positive and negative sign. So let's do it together. So let's put this on the number line, the electrode potential of copper to copper, which is 0.337 volt. Then first let's do the silver chloride. What is the electrode potential of this electrode versus silver chloride electrode? So basically you just need to know. So this is a distance 0.337, but in order to convert to silver chloride electrode, you just need to know the distance, this distance, right? How should I do this? In order to get this distance, which is the electrode potential of copper against the silver chloride, how should I find this number? Copper, yeah, someone say copper minus silver. Yeah, that's right, kind of right. So you know that this gap between the hydrogen electrode and the silver chloride is 0.337. So yeah, to find this distance, you just subtract it by the electrode potential of your new reference electrode. So it is, right, 0.337 volt minus 0.199 volt. This is a silver chloride. So yeah, use your calculator. So your electrode potential of the copper to copper electrode against silver chloride is 0.137 volt. Similarly, to find this number for the saturated calomel electrode, what is the electrode potential of copper to copper against saturated calomel electrode? So you do the same thing. You subtract 0.337 by 244 by 0.244, which is the electrode potential of calomel electrode, and then you get 0.093 volt. All right, so this is the example on the conversion. So let's do the example 2.2 together. This is a little bit more confusing because now I'm asking you to do it for the zinc electrode. And if it's in the exam, you should be able to pull this number from your table by yourself. But someone may remember this is minus 0.763 volt versus She, right? Versus She. So now to make it a little bit easier, you can just draw the number line as well. Yeah. So this is She, this is silver chloride, silver chloride, and this is calomel, and this is your zinc electrode. So basically, you can find the distance, yeah, for the silver chloride and for the saturated calomel, but your number is gonna be negative, right? Because it's on the left-hand side. So you can do this like to visualize and do this together, or you can just do the math. For example, let's do silver chloride first. Let's do this. So the electrode potential of zinc against silver chloride is gonna be minus 0.763 minus 0.199, right? This is this number, minus 0.199. For the copper example, we subtract it with 0.199, so this is the same thing. So this is going to be 0.763 minus 0.199 volt, which is going to be, I hope I pull the right number, this. Minus 0.962 volt. What about the versus calomel, versus calomel. You do the same thing, right? You subtract it with the electrode potential of the saturated calomel. So this gonna be minus 0.763 again, minus 0.244, and you get minus 1.007 volt. So basically, yeah, this is it for this example. Any question for this one? This is kind of easy. So let's do the more complicated one. Example 2.3. The example 2.3 asks you that an unknown half cell has electrode potential of minus 0.299 volts against silver chloride. Now you're given potential is against silver chloride. So let's convert it to hydrogen electrode and calomel electrode. So again, like to help your calculation, you can draw the number line. This is your unknown half cell, right? Minus 0.299 volt, and it is measured against the silver chloride, and you get this number. So first, let's find this distance. So what is the electrode potential against She? Against the She. But what we know the electrode potential against silver chloride. And we know that this number is found from subtracting the electrode potential that against She minus the electrode potential of silver chloride. And you know that this number is given minus 0.299 volt equal to this number we don't know yet. And this number is 0.199 volt. And do the algebra, you get this minus 0.100 volt. And this number is, of course, against the She, right? This number is against the She. It is basically this distance against the She. Now, once we know this, then you can find the one versus calomel electrode. The one versus calomel electrode is going to be similar. So it's equal to the electrode potential against the hydrogen electrode minus the electrode potential of the calomel. So it is, we just find like minus 0.1 volt minus 0.244 volt. So you get minus 0.344 volt versus calomel.